Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been going through the chapter on bondings in solids as well as X-ray diffraction, which form part of the paper on physics of materials. And so, this will be the lecture 13, and in this lecture we will be seeing mostly as to how X-ray diffraction can be used or has been used to study the nature of the bonding in solids as well as the atomic arrangements and so on. The contents of this lecture are as follows: the calculation of the wavelength of copper K alpha radiation using the simple Bohr atom model, the Laue method used in X-rays, Bragg's law, then the primary uses of X-rays and the types of cameras used in X-ray diffraction studies. And we look at the simple hydrogen atom. Now, why are we looking at the hydrogen atom? Because in the hydrogen atom, you know as to how to calculate the wavelength emitted when the electron is excited and when it is de-excited. And you have the electron in the hydrogen atom, there is only one electron, as all of you know. It is excited to the level, the ground state n equal 1 to 2, or you can have excited from 2 to 3 also. When the energy of the electron is in the n equal to 3 state, then it will come down to n equal to 2 state. When during this, when the electron is jumping from third quantum state to second quantum state, there will be emission of photon. The energy difference will be coming as a photon, and the energy levels are given by an expression of this kind. As all of you know by now, the energy levels are given by the expression minus 13.6 divided by n square multiplied by Z square, so many electron volts. In the case of hydrogen atom, Z is 1. So, the energy levels will be given as 13.6 or minus 13.6 is the binding energy, 13.6 divided by n square, where n will take values 1, 2, 3 and so on. N is 1, you know, the K shell, L shell and so on. Now, let us apply the simple hydrogen atom to the case of the copper crystal. How can you may ask the question, how can you apply the atom to the case of crystal? What I do now, from this hydrogen atom I go to copper atom, and I will show, because they are the inner shells, I am talking about the inner shells, the calculated emission energy of the emitted photon will not be very much different from what you calculate in the case of a crystal. So, I will understand these things in the, as time goes on. I told you in the last lectures that you are mostly concerned about the K alpha radiation, the copper target, or the K alpha radiation, the molybdenum target also. These are the primarily we are making use of the K alpha radiation to probe the arrangement of atoms in a solid. You use the copper target, right. Now, therefore, you have the copper atom, instead of copper target, solid copper, you look at copper atom. Okay. It is a simplistic approach, a copper atom, in which how do you get K alpha radiation? The K alpha is coming here. How do you get? You look at the K shell and the L shell. From the L shell, the electron is jumping to the K shell. Now, what happened to the electron in the K shell? The K shell electron have been knocked off, have been dislodged. Prior to this emission, first what you do is you send an incident electron, as you know, you dislodge or remove the electron in the K shell. Then when the atom has lost the electron in the K shell, then the electron in the L shell will jump to the K shell, because the K shell is empty. So, the electron in the L shell will be jumping to the K shell. Now, in this process, the difference in energy will come out in the form of a radiation. The wavelength of this radiation is the so called K alpha line, you get a K alpha line. So, let us look at the copper atom, and we will calculate the wavelength of this copper, the K alpha radiation in the case of copper atom. Then we will compare what is the K alpha radiation experimentally determined for the copper target. That is, we are going to compare the atom and the solid copper. Okay. Atom and the solid copper, the difference, let us see how it looks. Okay. Then how will you calculate now? So, the K alpha radiation is due to the transition n is equal to 2 to 1, as I told you. From K shell it jumps to the L shell. K is n is equal to 1, L shell is for which n is equal to 2. Therefore, the transition is from the L shell to the K shell. The Bohr's frequency condition, as all of you know, it is given as E 2 minus E 1 is equal to h nu, or E n minus 1 is equal to h nu. H nu is the energy of the outcoming photon, right. When the electron is jumping from K shell to the L shell, the frequency nu is the frequency of the emitted photon, the energy difference is coming out of the photon, that will be h c by lambda, where c is the velocity of light and lambda is the wavelength of the radiation. So, you have E k minus E L to be equal to 13.6 multiplied by n square is Z square is 29 square, Z is the atomic number of copper is 29, right. We have the formula here, Z square. So, Z is for copper, Z is 29. So, you substitute 29 square, then what do you have? You have instead of n square, you will be having 1 by n 1 square minus 1 by n 2 square. N 1 square is n is 1. So, 1 by 1 square minus 1 by 2 square, 1 by 2 square is 1 by 4. So, this is what you have as the for the difference in energy between E k and E L. So, when you have this particular thing in the bracket will become equal to simply 3 by 4. When you do the calculation, that comes out to be 1.446 angstroms. So, remember, in the case of a copper atom, when the electron is jumping from the L shell to the K shell, the wavelength that is coming out during this de-excitation, the jumping of the electron from L shell to the K shell, the wavelength emitted will be 1.446 angstrom. Now, we are not talking about the atom actually. In the case of X-ray diffraction, you are using a copper target, a solid copper. Now, for a solid copper, the wavelength that has been found to be experimentally that has been found is 1.541 angstrom instead of 1.446 angstrom. The beauty which should be appreciated is, supposing somebody asks a researcher or a ordinary student, what is the wavelength of how will you calculate the wavelength of copper K alpha? Copper K alpha means the copper target, solid copper. And the simple thing what you have to do is, instead of looking at the whole solid copper means you have got copper atom and copper atom, many atoms, right. Copper is crystallizing in the face centered cubic. So, every atom is surrounded by how many FCC means the coordination number will be 12, the 12 atoms will be there, and so 12 and then the next layer and so on. Several atoms will be there, it is a many body problem, right, several atoms are there, their influence on this particular atom, a reference atom should be taken into account, but without doing that complicated business, you are looking at a simple copper atom and you calculate the wavelength emitted when the electron is jumping from the L shell to K shell. Now, a simple atom, it comes out to be 1.446, it is not a bad thing. In a solid copper, it will be 1.541. So, instead of 44, you got 54. So, in a simplistic approach of calculating the copper K alpha, and this can be done for molybdenum. What will happen to molybdenum? In the case of molybdenum, the electron in the K shell is much more deeply buried. Deeply buried means there will be the K shell, and molybdenum has got a higher atomic number compared to copper. Then you go to tungsten or molybdenum or maybe the atoms with higher atomic numbers. The higher the atomic number, then the K shell will not be very much influenced by the other electrons in the other shells or the other atoms. The neighboring atoms will have very little influence on the innermost electron, the K shell or L shell. Therefore, the perturbation or the influence caused by the electrons in the outer shells compared to the electrons in the inner shell, and as well as the atoms, the adjoining atoms on the reference atom will become much smaller in the case of molybdenum and tungsten and so on. Therefore, compared to the case of copper, the wavelength coming from a simple copper atom and a solid copper will be the agreement is fairly good. You go to molybdenum, the agreement will be much better. Now, this is a very important thing why I am telling this. Even a researcher, I mean all researchers should be understanding as to how one arrives at 1.541 angstrom as the wavelength of copper target. Everybody will tell what is the wavelength that you are using in the case of copper target. It is 1.541 angstrom unit. How do you arrive at that? Okay, how do you calculate that? Using a simple Bohr atom picture, I am showing how you can get value, which is of course very near. The difference is due to the fact you are doing the case of atom, the other one experimental value is the case of the solid copper. So, the comparison should not be will not be accurate, right. It will be to a large extent the agreement is said to be fairly good, and one should have an idea as to how to do the calculation or how do you arrive at this value, one should have an idea. This is a very important aspect. Then we will move on to the Laue experiment, which was conducted by Max von Laue in 1912. Used a single crystal to obtain the X-ray diffraction pattern. You got a tube, X-ray tube, and you got a collimator. Now, the X-ray wavelength which will be coming will be like this. If you are using a copper target, the wavelength will be 1.541 angstrom. Okay. That is the thing that I am trying to show here. Okay. So, you got the copper target, then the collimator, then the X-ray beam of this particular wavelength 1.541 angstrom will fall on the crystal and giving rise to the spots, the so called Laue spots, which can be obtained on a film, X-ray film. Okay. That is what was done by von Laue in the year 1912, and he used a single crystal, and this is the Laue pattern, right. You have got the film here, you get a pattern, the spots will be here. Max von Laue put forward the conditions for scattering maxima. They are the so called Laue equations. Let us not go into the details of Laue equations which are used to understand as to how the dots are obtained, right. That is Laue spots have been obtained, and let me show you again the Laue pattern. The Laue pattern will look like this, right. Now, you may ask the question, from this pattern what do you obtain from the Laue pattern, right. The Laue method, as you know, is mainly used to determine the orientation of large single crystals. So, when you have a large single crystals, the orientation of large single crystals can be obtained using the Laue method, while the radiation is reflected from or transmitted through a fixed crystal. You can have either a reflected pattern or a transmitted pattern, right. I will show you in a little while how where the crystal is kept and where the film is kept. There will be film kept here and here. So, the diffracted beams form array of spots that lie on curves on the film. Now, the X-ray diffraction occurs like this, right. How do you explain X-ray diffraction? I will be going through the Bragg's law, the father and son. The credit goes to the father and son, W. H. Bragg and W. L. Bragg, who gave the Bragg's law, wherein what I want to tell you is you have the X-ray beam coming like this, right, and it is incident on crystal or a crystalline plane, right. It is a crystalline plane and is called a reflected beam or diffracted beam, right. This is a this is how the X-ray diffraction, in a copper target is kept. An incident electron comes here, it excites the electron in an atom to go to the electron is dislodged, the electron in the K shell is dislodged, removed, and the electron in the L shell comes to the K shell, right. That gives rise to K alpha radiation in a solid copper, right. That gives the wavelength, now the copper K alpha. But instead of taking the whole solid, I showed you that how you can calculate the wavelength emitted in case of a isolated copper atom. The difference is not very much, but of course, one should know as to how to calculate theoretically in a simplistic manner the wavelength of the copper K alpha radiation. The second thing is I was talking to you about the Laue pattern, how Laue got the spots. He showed that every crystalline plane acts like it obeys the Bragg's law, it gives rise to a diffracted spot, right. That is what you observe here. You have got a X-ray beam coming here, it is incident on a crystalline plane. In a crystal, in a crystal there will be number of planes, right. There will be a plane here, another plane here, another plane, or you can have a set of planes. You have got a plane here, or you have got a plane here, plane here. Okay. So, there are the crystalline planes. A crystalline plane is one in which you have got number of atoms. You have got atoms here, atom here. So, this plane that carries number of atoms is called a crystalline plane. So, this is a crystalline plane wherein there will be number of atoms. Now, the X radiation that is coming here of wavelength, if it is from copper target, it will be the wavelength will be 1.541 angstroms. This wavelength lambda that you have got here, it moves in this direction depending upon the plane, right, the position of the plane or the angle that it subtends, then it will give rise to a diffracted beam, right. You get the X-ray diffraction. I will give the details a little later. So, this is how the X-ray diffraction occurs, right. You have got an incident beam and this is a plane which diffracts the X-ray and the diffracted beam goes in this direction, right. This is so called the basic principle of X-ray diffraction, which obeys the so called Bragg's law. Now, coming back to the Laue method, the Bragg angle is fixed for every set of planes in the crystal. I will show you the Bragg angle and things like that. So, the Bragg angle will be fixed for every set of planes in the crystal. Each set of planes picks out and diffracts the particular wavelength from the white radiation that satisfies the Bragg law for the value of d and theta involved. So, in the Bragg's law, you will be having the interplanar separation d and the theta, that is the degree which the grazing incidence, and so the satisfying that these two, then the diffraction will occur, right. In the you have the back reflection, the Laue method. So, where do you have you got a X-ray beam here, right. you got a single crystal. Remember, in the Laue method he used a single crystal, right. The single crystal is here, the X-ray beam passes through this and you got a single crystal. The X-ray film is kept here. Now, this is called the back reflection. So, the X-ray beam which is coming here, it is incident on the single crystal. It is the planes which diffract or reflect the X-rays in this direction, it is called the back reflection. So, in this back reflection method, the film is placed between X-ray source and the crystal is here, right. The X-ray film is kept in between the source and the crystal, the film is kept, and so the X-ray beam comes here and it is incident, and back reflected beam, it is incident on the film, and the spots that you get, right, are shown here. They obey the Bragg's law. One side of the cone of Laue reflection is defined by the transmitted beam. I will come to the transmitted beam later. The film intersects the cone, right, with the diffraction spots generally lying on a hyperbola. So, you got a X-ray beam. Now, this X-ray beam is reflected and or diffracted rays which are coming in the backward direction, the back reflection, they give rise to the spots. The spots are found on the curve, this is called the back reflection, and there is the spots to be shown here, right. In actually the spots to be seen like this. The point is the symmetry of the Laue spot pattern, from the Laue spot pattern, it reflects the symmetry of the crystal, right. The symmetry of the crystal will be decided by the symmetry in which the spots are found. So, let me tell you again, the symmetry of the Laue spot pattern reflects the symmetry of the crystal when viewed along the direction of the incident beam. Laue method is often used to determine the orientation of single crystals by illuminating a crystal with a continuous spectrum of X-rays. So, what should you remember now? The first point is you are using a single crystal, right. The second point is you are using a continuous spectrum, right, white radiation, a continuous spectrum, not a copper K alpha, it is a continuous spectrum, the white light is used. So, you get the diffracted the spots are obtained here. Now, this Laue pattern or from the Laue diffraction, the orientation of the crystal alone can be obtained, right. It cannot be used for the other things like studying the crystal structure and so on, right. Only the orientation of the crystal can be obtained. So, the two things are the usage of single crystal and white radiation. Okay. And so, in the Laue pattern you make use of single crystals, then continuous spectrum X-rays, that is what I told you, you have the white radiation or a continuous wavelength. Okay. Then the symmetry and orientation of crystals can be obtained, right. Symmetry, the orientation of the crystal can be in general they are obtained by the Laue pattern. Now, what is the difficulty in obtaining the crystal structure? We will come to that point. The crystal structure determination by the Laue method. The Laue method is mainly used to determine the crystal orientation. As I told you just now, it is mainly used to study the crystal orientation. Although the Laue method can also be used to determine the crystal structure, several wavelengths can reflect in different orders, because you are using a continuous spectrum. There are several wavelengths which can reflect the different orders. You know, order means you have got n equal 1, n equal 2 and so on, from the same set of planes with the different order reflections, they get superimposed on the same spot in the film. Thereby, it causes the difficulty. This makes the crystal structure determination by spot intensity difficult. On the same spot, the the reflection coming from different planes, because of the different lambda values, different wavelengths, they will be lying on the different same spot, right, same spot or very near to the spot, and so it will be difficult to distinguish and determine the exact crystal structure of the material. You want to study the crystal structure of gold or copper or iron. So, the crystal structure cannot be obtained because you are using a continuous beam, right. So, the rotating crystal method, it is the method that overcomes this problem, wherein you will not be using a continuous beam, you will be using a polycrystalline material, and again you will be using a you will be using a single wavelength X-ray beam, right. You won't be using a continuous beam, right. Here you are using a continuous beam, right. Okay. But that is not the case in the case of powder diffraction, things like that. And so let us now move on to the Bragg's law. Now, the credit goes to the father and son, as I told you, W. H. Bragg and W. L. Bragg. They gave the simple expression which is named after them, the so called the Bragg's law. So, the Bragg's law, what it says is simply you have got a crystal, as I told you, crystal contains a set of number of planes, right. What is a plane? A plane is one in which you got atoms arranged in a periodic manner, right. You got atom here, atom here, atom here, and so on, right. The atoms arranged in a periodic manner. Now, you have the incident beam. The incident beam gets reflected or diffracted, right, reflected, and you know the X-ray beam coming here and falling on the plane below this plane, it also gets reflected. So, something like the angle of incidence is equal to angle of reflection, and this theta is called the grazing incidence, right. The grazing incidence, that is the angle between the incident ray and the plane which contains the atoms, this is theta, and if this is theta, this will be 90 minus theta, right. You know, this will be, you know, this will be, if this is theta, obviously this should be, because this is a right angle 90 degrees, and so this will be 90 minus theta. If this is 90 minus theta, then this should be equal to theta, right. This should be equal to theta, and so the vertical component here, if this is theta, so the vertical component should be d sin theta. So, this will be d sin theta, this will also be d sin theta. So, what is the path difference? You know, in optics there will be constructive interference between any two rays of light or any two beams. The path difference should be what? It should be integral multiple of lambda, right. The path difference should be integral multiple of lambda. Therefore, what is path difference? You just look at this beam, the beam comes here, goes like this, right. Now, here as far as this beam is concerned, it travels an additional path, right. It when compared to this, right, it travels a path d sin theta, another d sin theta. So, the path difference between this light ray and this light ray, that the electromagnetic radiation, the two X-ray beams, the path difference will be 2 d sin theta. The 2 d sin theta should be equal to lambda or integral multiple of lambda. The Bragg's law says the path difference should be integral multiple of lambda, it should be n lambda. So, 2 d sin theta will be n lambda. So, W. H. Bragg, that is father, and William Lawrence Bragg, the son, developed a simple relation for scattering angles, now called the Bragg's law. Now, Bragg's law is of immense use for all the people who are doing material science, or especially those who are dealing with X radiation, X-ray diffraction. This forms the fundamental law, Bragg's law. So, the Bragg's law simply states 2 d sin theta will be n lambda. What is d? D is the interatomic separation or interplanar separation. You have got one plane here, another plane below this. So, the distance separating the two planes, you have got one plane, another plane, the distance separating the two planes is d, the interplanar separation. Okay. Then theta is the grazing incidence, right. Okay. And lambda is the wavelength, n is the order number, order is the first order or second order. In the case of diffraction grating, all of you know, you look at you have the incident ray coming through the collimator, then it is incident on a grating, and then you get through a telescope you can see the first order pattern, the second order, right. So, order n is 1 is the first order, then 2 is the second order. Okay. So, n is the order number. So, here you see the Bragg's law, another view in detail. Now, let me now summarize what I told you so far, the X-ray wavelength can be calculated using simple Bohr picture, even though it may not be very accurate, because you are using, think of an atom and determining the X-ray wavelength when the electron is jumping from the L shell to K shell, then so that it gives a approximate value for the solid copper. Cell dimensions of crystals vary from 2 to 5 angstroms. That is the reason why you make use of X-rays. Bragg's law is of immense use, as it gives the lattice parameters, the distance separating the two planes and so on. Laue method can only give the orientation of the crystal, okay, not the crystal structure, only the orientation can be given by the Laue method. Now, we will pass on to the question session. How will you calculate the wavelength of K for radiation for copper? That is actually solid copper, but of course, you are not doing solid copper for the atomic case, right. What is Bragg's law? What do you understand from the Laue pattern? What are the types of cameras used? With this, we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.